If you have not already done so, please go watch my video about parent functions and their attributes. Otherwise, you're going to be very confused during this entire video. You really need to know what the parent functions look like. For example, quadratic. You need to know some coordinates of them. It'll make your life so much easier when you go to actually apply transformations to a quadratic, for example, knowing that it has a coordinate at 0, 0, 1, 1, and negative 1, 1. So that's just a piece of advice before we begin. But let's go ahead and dive right in. I'm just kind of going over some equations at random, so there won't be any rhyme or reason to it, but you'll see a lot of different examples and hopefully it'll help. Let's start with something, a quadratic, for example. Let's imagine they wanted you to graph this equation right here. Well, the first thing you need to know is the parent function and what it looks like. So this is my quadratic parent function. I'm going to go ahead and graph this and leave it up on the screen. I think it'll help with some of the concepts. Now, in terms of transformations, this negative in front is a reflection across the x. So immediately I know that this graph is going to do something going down now. It's not going to be going up anymore. Also, you need to know where your point of interest is. So for a quadratic, that's like a vertex. For a cubic, it's like your point of inflection. So you can get that by looking at your HK here. Remember, x's always lie in terms of transformations. So in my other video, I said you could take whatever is in the parentheses. Oop, it's a minus. You can take whatever's in the parentheses and set it equal to 0 and solve it. And that's going to be your new x coordinate. And then your y value here, this plus 5, it's telling the truth. So it's at 5. So basically I'm finding the vertex of my new equation. It's going to be at 3, 5. I'm going to go put a dot there. All right. Now, this 2 in front means this graph was vertically stretched by a factor of 2. So on my original, I went over 1, up 1 to get to my next coordinate. You kind of have to think, well, instead of going over 1, up 1, now it's going to be over 1, up 2. But remember, I have a reflection, so it's not going to be up 2, it's actually going to be down 2. So from my point of interest, from my vertex here, I'm going to go over 1, down 2, both ways. Then I can kind of just connect those dots and make it look like a quadratic and be done. That's what this equation would look like, the green line. Let's try another one. I've found with these, the way that students get good at them is to just practice over and over and over. Okay, this one's going to be a little trickier. Just because, and this is more of a rare situation, because teachers in general don't put too many transformations here right in front of the letter X. This is a horizontal compression. And so what's going to happen is, first of all, find your point of interest, which is going to be at, there's set your parentheses equal to 0, so 2x equals 0 and solve it. Then your y value is this right here, so 3. So I know my point of interest is at 0, 3. I'm going to go put a dot there. Now, this horizontal compression kind of does something weird to the graph. Instead of going up 1, over 1, or over 1, up 1, it's compressed by a factor of 2. So really it's like timesing by a half. So instead of going over 1, I'm going to go over just a half. Then I'm going to go up 1. Then I'm going to connect the dots, make it look like a quadratic, and I would be done with this equation. Again, this is kind of a weird scenario. You don't see a horizontal stretch or compression that often. They do happen though. So you should probably know how to do it. Okay, let's try a different function. Let's try something like a square root function. Another way they'll try to trick you is they'll give you something like this, where it's like we'll do a square root function of 9 minus x. If you're looking at this and you read it as 9 minus x, you've already lost the game. When I look at this problem, I actually see this. I see the square root of negative x plus 9. And so in terms of my point of interest, remember the parent function for a square root function looks like this. So my point of interest is 0, 0 on the parent, and then from there I go over 1, up 1 to get to my next point. Well, on this one, find your point of interest by taking this part and setting it equal to 0 and solving that. And then there's no vertical shift on this, so my y value would be 0. So now I know that at 9, 0, that's where my point of interest is. So it'd be like here. Sorry, it's not on the graph. And then from there was no stretch or compression. So basically all I have to worry about is this negative x part. The negative x part means it was reflected across the y-axis. So instead of going over to the right, it's going to go over to the left like this, but from my point of interest. So this right here would be my final answer. Let's keep moving. I want to make sure I show you a couple greatest integer, but we'll do one more simpler function first. So imagine something like this. Okay, this is an absolute value equation. So absolute value parent function looks like this. It's kind of similar to a quadratic, but not quite. Okay, and from an absolute value, my point of interest is 0, 0, and then from there I go over 1, up 1, either direction. So that's kind of what I'm keeping in my head as I move along on this problem. The first thing I would notice though is that there's a negative out in front. That's a reflection across the x-axis, so instead of going up, it's going to go down like this, but from your point of interest. So there's no shift or stretch or compression or anything on the x, so my x is going to be 0. And then on the y, it's minus 2, so my point of interest is at 0, negative 2. And then from there, this negative out in front just means go down instead of up. So it would look something like this. Okay, now for the really tricky ones, the greatest integer function. The weird part about these is there's multiple answers to a graph. Like I could draw a graph of a greatest integer function, and there's a ton of different possibilities for the answer of the actual equation. Let's start with something like this. Okay. Think about the parent function for greatest integer. It looks like this. All right, so looking at this, my point of interest is 0, 0. Now from there, I have an open circle to the right of it, and then I go over 1, up 1, and I have a closed circle there. That's kind of what I'm keeping in my mind as I proceed along this problem. So I would first find where my new point of interest would be. Take this, set it equal to 0, solve it. Look at my vertical shift for the y. So I know my point of interest, where 0, 0 was, is now at 1, 5. So I'm going to go ahead and put a dot there. Okay. There is no reflection. All there is this vertical stretch times 2. All that means is, from looking back at my parent function, from 0, 0. I went over 1, up 1. Well, now I'm just going to go over 1, up 2, and then put a dot there. So from my point of interest, I'm going to go over 1, up 2, put a solid dot. And that's how, and you can kind of work your way backwards to fill in more of the graph if you need it. But that's how I approach greatest integer. I'll do one more of these with a negative. So let's imagine something like this. Okay, remember my greatest integer function had 0, 0, 1, 1, and looked something like this. That's important to keep in mind. Now, I'm going to find my new point of interest, set this part equal to 0 and solve it. This shift here is my y value. So I know at -2, -3, I have a closed circle. But from here, I'm looking at this negative out in front. This is a reflection across the x-axis. So if you look back at my parent function here, instead of going over 1, up 1, I would go over 1, down 1. That's what this reflection is going to make this look like. So all I have to do is, from my new point of interest, right here, go over 1, down 1, put a solid circle, then make my graph resemble the greatest integer function. And that's applying transformations to parent functions.